The advent of low-cost plastic 3D printers has brought the layer-by-layer additive manufacturing of parts into the mainstream. However, more advanced industrial 3D printing processes are capable of additively manufacturing metal components. Unlike the low temperatures needed to soften plastics for printing, the processing of metals requires significantly higher temperatures. Some printing processes use a laser or an arc to melt powder or wire feedstock, which solidify layer by layer into the desired final shape. When using metal additive processes to manufacture commercial components, it's important to remember that the properties of a metal alloy and the performance of a final part are often influenced by the thermal history. For example, the thermal history in some additive processes consists of melting, solidification, and several reheating cycles, as already solidified layers are reheated during the formation of subsequent layers on top. During this process, a melted alloy cools within a temperature gradient, and directional solidification occurs. The result is the formation of small cells or dendrites originating at the solid-liquid interface. The size of these cells is controlled by both the temperature gradient and the solidification front velocity. Due to differences in solubility, the boundaries of the cells are often enriched in some elements and depleted in others when compared to a properly homogeneous alloy. For nickel superalloys, commonly used at high temperatures in extreme environments, this segregation can influence the number, size, and type of nano-precipitates that form. Our research aims to understand how the formation of these phases are influenced by additive manufacturing processes, which affect the strength and performance of potentially critical components. Using a nucleation site model, we are able to accurately predict precipitate size depending on the cell size and the number of available nucleation sites. This allows us to control precipitate distribution and size in our nickel superalloys, which is critical to the creation of stronger materials and wider adoption of additive manufacturing processes in industry.